Hey guys, what's going on? So today we're going to be starting Chern Simons theory. So Chern Simons theory it's a theory in physics. It follows up on gauge theory. It's quite advanced. It's a topological field theory. It's going to bring together the idea of differential forms, differential geometry, topology, algebraic topology, and all this stuff. And it's going to put all of it together into one cohesive theory, if you will, on physics. It's not exactly a cohesive theory in terms of like string theory or anything like that. It doesn't really explain everything in the universe, but it's going to do a pretty good job at telling us a lot of things about electromagnetism. So what is Chern Simons theory? It is a topological field theory. And what we're going to do in this first introduction video is we're going to really just talk about what exactly topology is and how exactly we want to get our mindset ready for learning a theory like this. So without further ado, let's go ahead and get started. We are talking about Chern Simons theory. So this playlist is going to be a discussion on Chern Simons theory. But before we dive into the depths of such an advanced theory, I'm going to provide an introduction first. Chern Simons theory is what's known as a topological field theory, or a TFT. These theories propose actions that are independent of a metric. So that's what it means to be a topological field theory at its core. You have an action that does not have a metric, okay? That does not depend on a metric. Let's go back to what this means. We want to really just we want to understand what it means to not depend on a metric and to depend on a metric. And we're going to do this by looking at a photo, just a simple photo. So if you're into Fourier transforms and all this stuff, whenever you Google Fourier transform of an image, this is the image you get of this woman, okay? Random picture of a random woman, okay? But what I'm doing here now is, okay, you have this picture. Suppose in one hand you have a ruler, and this is the ruler is the metric by which you use to measure distances on this picture. So you can measure, say, the perimeter of her hat, right? I'm going to change the thickness of my pen. You can measure the perimeter of her hat, for example. You can measure, say, the length of her nose. You can measure the curvature of her shoulder. All this sort of stuff depends on you having a ruler, putting that ruler on this photo and measuring these distances, okay? These distances on this photo are metric dependent. It requires that you have a ruler to be able to measure these things. And in physics, we have rulers that are at the core of physics. You have rulers and clocks, okay? Now in general relativity, to the space-time, you need the clock, right? So if you want to measure rates of things, accelerations of things, you need the clock as well. So really at the core of everything here is you have the things that depend the things that depend on you having a ruler and a clock at your disposal are things that are metric dependent, right? So your metric is the ruler and the clock. Are you measuring in seconds? Are you measuring in centimeters? Are you measuring in meters? And so forth. So these things are metric dependent. Okay. There are some things, however, that you do not need a ruler to measure. Suppose there are some holes in the photo. Suppose I punch some holes in the photo, and all you have to do now is count them. The number of holes in the photo can therefore be thought of as a topological feature of the photo. The resolution of the photo might be another one. So, and the orientation of the photo as well. So suppose we now have the same photo, but we hole punch it. All right, so we've hole punched this photo. We have a total of 3 holes. Okay? That's a topological feature of this photo. Okay? 3, the number of holes. And this is going to be something we're going to want to come back to, right? The idea of topology is this thing, is this study of things that are sort of invariant under any sort of transformation, right? Or under a topological transformation, if you will. And the number of holes is exactly that. Ignore my dog. He barks a lot. He's a Great Pyrenees. Let's just keep on going here. We now want to take this analogy of a photo and talk about physics. Okay, so what are some topological features in physics? Electron spin might be a good example. You don't need you don't really need a ruler or a clock to measure the spin of a particle. Electromagnetic charge and color charge might also be other examples of topological features in physics. Let's get a little bit more abstract. Consider a spatial manifold. Okay, this is the spatial manifold. What do I mean by that? A spatial manifold is really just three-dimensional space for right now. Let's just think of this manifold, this thing that I'm calling a manifold, as just three-dimensional space. You can move forward and back, left and right, up and down, right? Forget about time for right now. All right. So we're going to consider a spatial manifold as being the future boundary of a space-time manifold. Okay, so what I'm doing here is you move in space and time, but at the boundaries of space and time are just space, right? So at one moment in time, you're at some state, then you travel through time, you travel through that time, and you travel through that space, and then at the boundary again, at some particular time, you're just in some space, right? So we'll go over this a little bit more, but the idea is space-time has boundaries, and the boundaries are one dimension less than the inside of the volume. Okay, you can forget about that if right now. We're going to slowly introduce this as we go on. We then do a path integral on the space-time manifold as a function of the boundary values on that spatial manifold. And again, we have some images that we'll get to really, really hone in on this idea. In general, in field theory, an integral over a manifold of one dimension more, the past, is a way to prepare a state in a Hilbert space in our spatial manifold. Okay? Again, what the idea is, you start at some point in space, then you travel through that extra dimension of time, and you end at some point in space again. So that extra dimension of time, that extra dimension constitutes the volume of the object. Again, ignore the dog. So let's try to visualize this. It's fairly easy to do this with a two-dimensional spatial metric. So suppose you're on some field, okay? You're standing at this blue dot, and you want to get to this green dot. There's multiple ways you can get to the green dot, right? So you get from blue dot to green dot, and you could take any one of these paths. Now suppose we hole punch this two-dimensional field. The topology of our space places a constraint on how we get to the green point. So consider the following picture. Now we are at blue dot again. We want to get to the green dot. But now there's a hole in the way. So the number of holes is going to tell us, or is going to say something about what paths we can take as we go from blue point to green point. Okay? It's going to put a restriction on how many paths we can take. And so we can see here that there might be some relationship. Again, my apologies for the dog. He is a Great Pyrenees. He barks at everything. Just please ignore him. There might be a relationship between some path integral on some space-time and the topology of that space-time as well. This is what this whole series is going to be about, right? This is going to be about discovering a relationship between path integrals, topology, all within the context of electromagnetism. Okay. And we're going to stumble across other concepts along the way, because we need to talk about homotopy, we need to talk about cohomology, homology, other areas in topology, if we really, really want to get a firm understanding of what's going on here in Chern Simons theory. We're going to have to talk about gauge theories and all this kind of stuff too. Alright. So in our previous example, we considered moving only in a 2D plane with a hole in it. So we live in a three-dimensional space, though. So we're not really moving in 2 dimensions. We actually live in 3 dimensions, and so our picture should be more like this right here, right? Where we have some object that's 3-dimensional, and if we want to get from point blue to point green, we could take any one of these paths, but we have to avoid the hole. Okay, we don't want to fall in a hole, right? That's not good for us. So again, the holes are going to be important here. This is the number of paths really sort of depends on how many holes are in this space, okay? So in modern physics, now we have to abstractify our mind a little bit. We're going to allow for these holes to change. So typically we might see pictures like this, right? So here's that 2D space-time we were talking about, where we had, like, say, some green hole or some green dot, and we had a blue dot, say over here, and we want to get from the green dot to the blue dot, but to get from the green dot to the blue dot, so here's our blue dot up here, and here's our green dot here. Well, if we want to get from green dot to blue dot, we have to travel through time. So one of our paths might look like this. Okay? If we don't move at all, our path might look like this. Right? We might have a path that looks like this if we want to get from green to blue. So there's multiple different paths we can take within this volume. Okay? And the number of holes we're going to have to avoid, because again, we don't want to fall in a pit, right? So the idea here is that we now have a picture in our heads on how we want to construe the current situation. We have 3D space, and then we travel through time, the extra dimension of time, to get from this space to this space. The boundaries of this thing are 1 dimension lower than the middle portion, because in order to get from one place to another, we need to travel in space and time. So if we connect the holes, then our picture looks something like this, where we have a final Hilbert space, an initial Hilbert space. We'll talk about Hilbert spaces later, but in short, Hilbert spaces are ways that we can construct states, okay? Or it's this sort of abstract notion of a vector space that enables us to describe states, okay? So a path integral then might look like the following, right? We need to sort of avoid this thing here, okay? So path integrals will look like this then. One thing I want to point out also is that you're going to see this picture, not just in Chern Simons theory, we're going to see pictures like this in string theory as well. String theory being, like, suppose these are strings then, and they travel and they merge and they become one string. These ideas we'll talk about later when we talk about string theory, or in our quantum gravity playlist. All right. It's quite easy then to see that the holes in our Hilbert space are states that cannot be accessed. In physics, these states correspond to properties of materials, not materials, spelled that wrong. Materials that remain unchanged under continuous deformations. In the past, we've talked about different types of transformations. So we've talked about Lorentz transformations. We haven't really talked about coordinate scaling and metric scaling. This is going to be something we talk about when we talk about conformal field theory, which is also something that we need to talk about. But we've talked about Poincare transformations as well. This is what those transformations look like. This is what generators for the transformations look like. We're going to get into a lot of this later. I'm just sort of getting our feet wet, if you will, with notions of transformations here. And last but not least in this video, I want to cover some actual physical applications of this before we move on. So when we're talking about deformations, we're including all of the above types of transformations, including transformations that don't include tearing objects. Okay? That's going to be important when we start talking about topology. The point here is that we are interested in the properties of materials or objects that depend on the shape of the object. We can bend and fold and warp some space as much as we want. We should still have the same properties after all these transformations occur, though. Physics always stays the same no matter how much you look at it. That's sort of the point. You can bend your notion of reality as much as you want, but the physics is always going to stay the same. And so that's sort of a very general notion of what how topology is going to help us. Topology is going to say, what are the bending and folding and the warps and all these things that you can do to some space so that you could still maintain physical properties of space-time. Okay, so here's some examples of topological notions that occur in physics. Superfluids, right? So fluids that have no viscosity at very cold temperatures undergo some topological phase transition when freezing into ice, right? So you could sort of think of this as a fluid that has some property, some topological property, again, that doesn't depend on a metric. So it's like the number of holes, if you will. But then the topological phase transition is going to say go from 2 holes to 1 hole, right? So the properties fundamentally change under this phase transition. So a phase transition can be thought of as a topological transformation of this fluid. The quantum Hall effect. So the quantum Hall effect, so at the quantum level, the resistance of a material jumps in discrete steps, and this was only determined by the shape of the object, not the material itself. And so the shape, again, holes are sort of the properties of shapes, how many holes are in the shape. If you have 2 holes in the shape, you have 3 holes in the shape, then the thing that has 2 holes has the different properties than the thing that has 3 holes. Okay? And so the quantum Hall effect really has to do a lot with the shape of some object and the properties, specifically the resistance of the property as it changes shape. Okay? So resistance in this quantum Hall effect is a topological feature of this physical phenomenon. Superconductivity. These objects carry current without resistance. And this current, so we talked about resistance in the Hall effect, the current, therefore, in superconductivity becomes a topological feature as well. The idea here is that when you have some space or some material, the superconductivity, what you end up seeing is that the conductivity occurs only on the edges of the object and not in the center. But we'll go into this a little bit more later. What we actually really want to go to in this is Chern Simons theory, and so I don't think we'll talk a lot about superconductivity, but I might throw it in as an extra video or something like that, or an extra 1 or 2 videos. And then topological insulators. These objects act as conductors on their boundary and insulators in their interior. There's similar notions between topological insulators and superconductivity. Again, we're not going to go too deep into them. I'm just sort of trying to justify this whole playlist, if you will, because fundamentally what physics comes down to is the real world, and we want to be able to understand how we can use topological field theories in the real world, and then we'll move on to Chern Simons theory. And then string theory, right? String theory, strings can take on different shapes, which dictates the vibrational patterns of these strings. Again, things that depend on shape, number of holes. This all comes down to topological variants or topological features of some object or some space. Okay. Chern Simons theory will take this idea of topology and apply it to electromagnetism. At the core of Chern Simons theory is the idea that we can develop a topological explanation to understand the dynamics of electromagnetism. This comes from its proposed action. So this is the theory, right? Whenever someone says, here's my physical theory of things, what they need to do is they need to hand you an action principle, right? They need to tell you, I think this action is going to explain everything that we know in the universe. And so you employ the Euler-Lagrange formulation and all this stuff, and and if you get the right equations of motion and all this, then your action checks out. So when someone says, here's my theory, here's my Chern Simons theory, here's my Hamiltonian, or something like that, or when someone says, here's my theory, what they need to do is they need to give you an action, okay? Or some Hamiltonian, okay? And it's going to take us some time to understand all this, but we're going to get there, right? What we have here is exterior derivatives. We have wedge products. We have, again, an action. We need to talk about an action. We have this proportionality constant, not going to matter that much. So manifolds. And again, we need to understand the concept of a manifold if we want to understand concepts in topology. But we're going to do this. We're going to go slow, but we're going to do this. We're going to make some headway, and we're going to really understand this theory. So what's important to note here is that this action does not depend on any sort of metric, which means that it's a topological field theory. Right? So we don't see a metric in here. We don't see G, or not Q. We don't see G, mu, nu in this metric. All right. So join me in this playlist as we investigate the world of Chern Simons theory. We're going to start our discussion with differential forms. So with that being said, I'll see you guys in the next video. Sit tight and get ready for the next video. All right, bye.